Welcome to the Platform Engineering Playbook podcast, where everything you hear is built, reviewed, and improved by AI, by me, and by you, the listener. This show keeps me, and hopefully you, up to speed on the latest in platform engineering, SRE, DevOps, and production engineering. It's a living experiment in how AI can help us track, explain, and discuss the fast-moving world of infrastructure. Every episode is open source. If you've got something to add, correct, or challenge, head to platform-engineering-playbook.com. You'll find all the content and a link to the GitHub repo. Open a pull request, join the conversation, and make the playbook smarter. Let's get into it.
Today, we're diving into Cloudflare's November 18th outage. ChatGPT went down, X went down, Shopify, Discord, Spotify, even Down Detector, the site that tracks outages, went down, all from a single configuration change.
And here's what makes this technically fascinating. It wasn't a cyber attack. It wasn't a DDoS. It was a database permissions change that caused a feature file to double in size and exceed a hard-coded memory limit in their Rust proxy. The whole thing cascaded from there.
20% of the internet. That's Cloudflare's market share. And this was their worst outage since 2019. Let's break down exactly what happened, because the technical chain reaction here is something every platform engineer needs to understand.
So let's start with the timeline. November 18th, 11:05 UTC. Cloudflare deploys a permissions change to their ClickHouse database cluster. This is routine stuff, improving how distributed queries handle access control.
And nothing breaks immediately?
Right, that's part of why this was so hard to diagnose. The first errors don't show up until 11:20 to 11:28 UTC. That's 15 to 20 minutes later. And even then, it's intermittent.
Which made them initially think it was a DDoS attack.
Exactly. They saw the traffic patterns, the error spikes, and their first instinct was, we're under attack. The status page went down around the same time for unrelated reasons, which made that suspicion even stronger.
So when did they realize it was self-inflicted?
The automated tests caught something at 11:31, incident call at 11:35, but they didn't identify the actual root cause until 13:37 UTC, over 2 hours after the first errors. And here's why. The failure was intermittent because the ClickHouse cluster was being gradually updated.
Walk me through that. Why does a gradual update make this intermittent?
So the bot management feature file gets regenerated every 5 minutes by a query running against the ClickHouse cluster. If that query hit a node that had the new permissions, you'd get the bad file. If it hit a node with the old permissions, you'd get the normal file. The system would crash, recover, crash again. It looked like flapping, not a config issue.
That's brutal from a debugging perspective. Okay, let's get into the actual technical failure. What went wrong with this permissions change?
Here's where it gets interesting. Cloudflare's ClickHouse setup has a default database and an underlying R0 database. Historically, their internal processes assumed that metadata queries would only return results from the default database. The new permissions change allowed those queries to also surface metadata from R0.
And the bot management query wasn't filtering by database name.
Exactly. It combined metadata from both locations, which meant every feature showed up twice. The feature file that normally contains around 60 machine learning features suddenly had over 200 duplicate entries from both databases.
And that's where the hard-coded limit comes in.
Right. Cloudflare's FL2 proxy, that's their new Rust-based proxy that replaced the old Nginx and Luajit stack, has a bot management module that pre-allocates memory based on a strict 200-feature limit. They normally use around 60 features, so there's plenty of headroom. But when the file exceeded 200, the system hit that limit and panicked.
A Rust panic. So it's not a graceful degradation, it's a hard crash.
The exact error was thread FL2 worker thread panicked, called result unwrap on an error value. The code was calling unwrap on something that should never fail, and when it did fail, there was no error handling, just panic.
Wait, they used unwrap on something in the critical path of their proxy?
That's the thing. This code path assumed the feature file would always be well-formed, because it's generated by their own systems, internal data, so it must be trustworthy. That assumption broke catastrophically.
This is the core lesson here, right? They treated internal configuration differently than they would treat user input.
That's exactly what their postmortem acknowledged. They committed to hardening ingestion of Cloudflare-generated configuration files in the same way we would for user-generated input. Internal doesn't mean trustworthy.
Let's talk about the blast radius. What actually broke when this panic happened?
So Cloudflare runs two proxy engines, FL2, the new Rust-based one, and FL, the legacy Nginx version. They've been migrating customers to FL2, so the impact split along those lines.
How so?
FL2 customers got HTTP 5XX errors, complete failures. The proxy crashed and couldn't serve traffic. FL customers, the ones still on the old engine, didn't get errors, but the bot scores came back as 0. Every single request got a bot score of 0.
Which means any customer with rules to block bots based on score.
Massive false positives. Their legitimate traffic got blocked because everything looked like a bot with that 0 score.
And Turnstile?
Complete failure. Turnstile is their CAPTCHA alternative, and it depends on this same bot management infrastructure. If you weren't already logged into the Cloudflare dashboard, you couldn't log in. The dashboard uses Turnstile for off.
So Cloudflare couldn't even log into their own systems to fix the problem.
They had to implement bypasses for Workers KV and Cloudflare Access around 1305 UTC just to get their own systems functioning. That's almost 2 hours into the incident.
Let's zoom out for a second. This is the third major cloud infrastructure outage in 30 days. AWS on October 20th with that DynamoDB DNS race condition, Azure on October 29th, now Cloudflare.
And here's what should concern platform teams. The number of outages isn't necessarily increasing. Cisco logged 12 major outages in 2025 versus 23 in 2024. But the blast radius keeps growing. More sites, more services depend on fewer providers.
Cloudflare serves 20% of websites. 35% of Fortune 500 companies use them. That's concentration risk at an infrastructure level.
The internet was literally designed to route around damage. That was ARPANET's core principle, no single points of failure. And we've built ourselves right back into exactly that situation in the name of efficiency and cost optimization.
So what did Cloudflare commit to fixing?
4 main things. First, hardening config file validation, like we discussed. Treat internal data like external input. Second, enabling global kill switches for features. They couldn't just turn off bot management at the edge. They had to stop the file propagation and manually deploy a known good version.
That's a big one. If you can't kill a feature instantly, you're at the mercy of your deployment pipeline during an incident.
Third, they're eliminating the ability for core dumps and error reports to overwhelm system resources. During debugging, the diagnostic systems themselves were consuming so much CPU that it made recovery harder. Fourth, reviewing failure modes across all proxy modules.
Let me ask the practical question. What should platform teams be doing differently based on this?
Start with your CDN strategy. If you're 100% on a single provider, what's your fallback? Multi-CDN isn't just about performance anymore. It's about blast radius containment.
That's a big architectural change for most teams.
True, but there are intermediate steps. At minimum, understand your dependency tree. Which third-party services could take you down completely? When Cloudflare went down, Shopify went down. When Shopify went down, thousands of stores went down. That's 3 levels of dependency.
What about on the code side? The hard-coded limits, the panic on error. How do you audit for that?
Look for anywhere you're using unwrap or expect in Rust, or similar patterns in other languages where you're asserting something can't fail. Then ask, what if it does? Do you have a fallback? Can you gracefully degrade? For config files specifically, validate size, validate schema, validate against expected ranges.
The intermittent nature of this failure, that seems like a pattern we should watch for.
Absolutely. Gradual rollouts are great for catching errors before they hit everyone, but they can also create these intermittent failures that mask the root cause. If you're seeing flapping behavior, consider whether a partial deployment is involved.
What about the observability angle? They initially thought this was a DDoS attack.
That's a great point. Your monitoring needs to distinguish between traffic spike causing errors and errors causing traffic patterns that look like spikes. Correlation isn't causation, especially during incidents.
Feature kill switches. How did you design those properly?
They need to be independent of your normal deployment path. If your deployment system is broken or slow or requires the thing you're trying to disable, you're stuck. Edge-level feature flags that can be flipped without a full deploy, that's the pattern.
The internal data is trustworthy assumption. That seems like it's everywhere.
It is. We validate user input religiously, but we trust our own databases, our own config systems, our own internal APIs. This outage is a reminder that the most dangerous bugs often come from the code that handles your own data, because that's where your guard is down.
Let's bring this back to the big picture. 3 major outages in 30 days, all from different providers, all from different root causes. What's the takeaway?
The question isn't whether your infrastructure provider will have an outage, it's whether you've designed your systems to survive it. Every dependency, internal and external, needs to be treated as potentially hostile.
That's a pretty adversarial mindset.
Defensive programming isn't about distrust. It's about acknowledging reality. This Cloudflare outage came from a routine permissions change to improve security. Good intentions, catastrophic outcome. Your systems need to handle that possibility.
So the fundamentals, validate everything, degrade gracefully, have kill switches, understand your blast radius.
And audit your assumptions. Somewhere in your stack, there's code that assumes something can't fail. That's where the next outage lives.
Sometimes the most dangerous code is the code that handles your own data.
Because that's where your guard is down.
That's it for this episode of the Platform Engineering Playbook podcast. Every topic, transcript, and summary you just heard lives out in the open at platform-engineering-playbook.com, where anyone can suggest updates or add insights through GitHub. If you've got thoughts, fixes, or new ideas, open a PR. And if you enjoyed the episode, rate us on your favorite podcast platform. We're always shooting for 5 stars. While you're there, give the project a star on GitHub. It helps others find and contribute to the Platform Engineering Playbook. This podcast is generated by AI, reviewed by AI, me and you, a community of engineers keeping our craft sharp. Thanks for listening, and see you next time inside the Platform Engineering Playbook.